All right, I'm working on adding uh, details to this low poly leaf. So here on the skirt, I took it off. This used to be on the skirt over here. So here's like these really like simple shapes, like this wing leaf and these rose petals. And I wanted to add more detail to them without adding more polygons. So they're all like really low poly. Like this one's only like 16 polygons. It'll be like 32 polygons. So I was trying to add details to it over here using the shader and Blender just to see what it would do. So I made this gradient. So there's only going to be black and white colors here, and the different ranges of gray. And then so this is going to be black is 0 and white is a value of 1. So and that's in here. That's this value. That's that gradient. So then that multiplies times this color here, which is the leaf color. It's going to be the leaf color. So this is like the average color. And it can be either darker or lighter depending on what it multiplies with. And that'll go to the base color. And that gradient also affects the normal map through this bump node. And also will affect the metallic. And probably, maybe I can make it match with the sheen tint as well. I think though this is not a good idea because the sheen tint is like really active at even low values, but we'll see what happens. Emission tempting, but no. All right, so I'll switch it back. I already started drawing, so this drawing right here is I'm gonna switch the nodes, and it's gonna go to this one. So this is what I drew here, and it's showing up over here. So this is without that alpha texture affecting everything, and this is with it affecting everything. So good. I was trying to emulate these leaves by Frida Kahlo over here, so it'll look. I just really like that it's like shadow. There's like light right here, light, and then it's bordered by darkness, and then like everything is like that. And like a lot of her paintings are this way. Like we know leaves don't actually look this way. Like leaves definitely do not look this way. But her methodology for art was that she wouldn't just draw things from one perspective. So she would draw things from like multiple angles because if you look at something from one angle and then from another angle, you might look at it specular art. You might look at it specular and see like a shininess. And so like these leaves, like this shininess shouldn't really be here this much. Like maybe it should be this part should exist and this part shouldn't exist. But since she examines things from multiple angles and then like overlaps them, it looks more real than real. Like it looks more real than real. Like leaves don't look like this, but this is like a form of hyper reality. And we kind of also do that. We also kind of do that in modern day with our new HD televisions because they actually sample the scene from like multiple different exposures and then overlap everything. So when we look at stuff in HDR, things don't really look that way. So like this painting is like a good analogy for the fakeness of our HD content these days because our HD content isn't really accurate to real life. Anyway, so here's a leaf. Oh yeah, also here too, like these twigs, like they don't like in real life they don't look like that either. And see this, there's like a little tiny hint of green in this little thorn, and like that would probably only be visible from a certain angle. And like roses also have like color gradients like that, depending on what side of the rose you look at it. Like near the thorns, it will look a little bit blue or a little bit more red. Like also the hummingbird here, see like they usually have very like iridescent scales or feathers on them. So depending on what angle you look at a hummingbird, like it should change colors. And that's really one thing that I don't like about PBR textures is that they're so flat and it doesn't really matter what angle you look at stuff because some things uh, like they should change colors depending on what angle you look at them. So we do have specular, like it's right here. We do have a specular, but it's not great. Like this usually only gives you one color, and then you go between that color and its normal color. So it's not really like It's not really shiny. It's not like a really a rainbowy effect. And there are effects that are uh like the little color changes that are like in oil inside of water. If you mix oil and water, you'll see like little ripples of rainbow, but it's not really like the way that like a hummingbird's feathers would change, or the way a fish scales would change, or the way that like because plants have like a glossy layer on them, and depending on what angle you look at them, like this should if this was a real plant, this would like really subtly change its color as well. And like even shadows have that. Like because of the type of scattering, I'm not sure if it's Raylene scattering or Fresnel scattering as well, but different wavelengths have different like they'll refract differently around objects. Like if light were to come around the edge of this leaf, it's mostly imperceptible to us, but even the bending of light around objects that are around sharp corners, it acts like a prism and separates things. So if you look at a really sharp shadow on a really sunny day, if you look at the edges, it'll like you should see a slight rainbow. It's really subtle though, and usually we don't really pay attention to it. And I really like Frida's art because like it incorporates some of those concepts because like the leaves, and but she doesn't do it with color. I don't even think they even discovered those effects back then. Yeah, that like because quantum mechanics is what discovered that shadows are full of colors. That like ironically, especially like if you have like a coin and the middle of the coin is gonna have a bright spot in the middle. Like those are all aspects of quantum mechanics that like weren't discovered until like the nuclear age. But for her, during her era, uh, this her looking at the specular from like different angles, like and then painting it all on this flat canvas is like it's more real than real. Like this is like more real. Even the cat, like some of these don't make sense because this light comes from this direction, and this light comes from this direction. So you look at the cat from the left, you'll get these. Look at the cat from maybe the top and the right, you'll get these. Or is it correct lighting? I don't know. But like that was her thing to look at stuff from like different angles. And so like I really want to work on a shader like that, and I kind of developed one uh, for now just on specular, but I really want the color of things to depend on the viewing angle, and I'm really not sure how I'm going to accomplish that. Anyways, back to what I was doing. I don't know, a long tangent on that one. So here's a leaf. Here's the leaf right here, and I paint on the leaf. Okay, I have white on the painting thing right now. I have white, and that'll mess up. That'll add normals and height and color at the same time. And I'm sure this is what Substance Painter is for, but I don't know how to use it yet. So, and I don't want to learn right now. So I'll get a squiggly line right here, and like the color is changed. Like, oh, see like how fancy that is, and it doesn't add any additional geometry to anything. Like, I'm sure the engine won't bitch at me if I add like textures. Well, I probably won't like that these are 4K textures. The other thing that I really don't like about normal maps and height maps though is that they don't change. They don't really change on based on a viewing angle. Because look at this, right? Like it's really two dimensional because the let me see if I can get an annotation. The normal map is this way, and like the height map and everything is just like in relation to the normal map. So it's just like a cosine right here, a cosine distribution. Like this is one, and this is zero. So depending on how you look at this, depending on what angle you look at this, you'll just get a different light value, right? Like if you look at it from, oof, I'm trying to get a good view of this damn annotation. Here we go. If your light value comes in through here and it's close to the one, then you'll get a bright value. If it comes through here and close to the zero area over here, like this is zero, this is like 0.5. It's not really linear though. You'll get a not as dark value, and then we have the normal map which like fakes like messes with this normal depending on like the normal map will say this is going to be more and this is going to be less, this is going to be more, this is going to be less, and then this cosine dot value is going to be more or less. But like what I really don't like is that it's so flat. Like it still produces like a flat texture because it's still based on normal maps like this, and like if you get like a really sharp angle right here, like it still looks flat. Like you're like there should actually be some depth. There should be some depth right here, like a little crevice. Like here's the leaf, right? Let me draw it over here. Okay. Let me erase some of these. Like this is my pet peeve with like current normal maps and height maps. Like I really want to like solve it, but like it's gonna take like way more data inside of a normal map, which can be done. I'm pretty sure it can be done if like I'll discuss that in a second. But like I was thinking to talk about this, but here we go. So like here's a normal, right? And the light beam's gonna come in through here, but the normal is like here, and like most of the weight for this normal, because the distribution for the dot product is usually like a cosine, so it's like this. So it's like these angles that are here near the top, they have way more power than the ones here. So this would be 0, and 360 would be like here. Like this is a polar map. So angles between like 0 and 15 degrees, they get so much more like variance. They get so much more of the value that like when you look at things from over here, because from these angles here, like this is so flat because like the there's no real space because the values are so shortened, because over here is 1, right? There's point 0.1, and from like point 0.7 to point 0.1 at these angles over here. So like that's a big multiplier because everything's multiplied. The dot product is normal times viewing angle usually, and like it'll go from 0 to 1. But over here at like from 0 to 15, like that's like this much of the range, and then there's only like point 0.2. There's like only point 0.2 left for all these little tiny angles. So when you look at things from like these sharp angles, like it looks flat. Like from the viewing angle of like 0 to 15 degrees, like from here, like this angle right here, like this triangle, like the normal map and the height map, they don't move like at all, and it looks like a really flat texture, and it looks like there's no point in even having a normal map at that point because it doesn't do anything. It doesn't really do anything, and like the the normal map can't even adapt to this because the normal map is not dependent on the angle that you're looking at. It's like even if you put a normal map on an object, it's like I think it's like a cone. Like it's like a cone. So like anything within this viewing angle, it'll be the same. Like if you're 15 degrees off this normal map here, or 15 degrees over here, or 15 degrees over here, like it treats it almost exactly the same. The normals are almost the same. And these extreme angles, like over here, if you view it through here, like through any of these, like there's no more data. There's no more data because from point 0 to point 1 is like all you get out of this dot product, and there's even though the viewing angle is really big, there's no data there. There's like no I don't know what to call it, granularity. So it looks flat when you look at things from a sharp angle. It's like it's just flat. It just looks like paper, and I hate that. Like I understand the limitation of like the way that things work right now, but I freaking hate that. And like I really want to like get more data into those data ranges. So I was thinking that we could like use some digital signal processing techniques to get more information out of the normal map. So with digital signal processing, you can actually okay, right now the way normal maps work is that they store information in the baseband. So what you see is what you get. Where like Like let's say this is frequency. Frequency, and here's 0 kilohertz, and here's like 1,000 kilohertz, and here's negative 1,000 kilohertz. Which, I mean, you can't really use. I mean, you could use the site actually with proper filtering, and like radio towers use it. Anyway, so we're here. Like the way that we read texture maps is here in the baseband. Like no modulation or anything. What is modulation? So modulation is where you put a signal on a carrier wave. So uh, in radio, like amplitude modulation is where we have a carrier wave. Like let's say this is 1,000, or let's say this is 20,000 kilohertz carrier wave. And then the message is not as high frequency. It's like a voice, or like let's just say it's like 1 kilohertz. So what you usually end up getting is the carrier wave on here, and then this can like travel over the air and receive a receiver somewhere. And like with different carrier waves, they can carry different messages over the same air. And so the way we talk as humans is in the baseband. Like we're just moving air, like the air, and then we listen to the air. Whatever someone says, we hear. But in radio, there's like different signals like overlapping, and like there's like a billion channels in there, or maybe like 1,000 channels, and like they can all be decoded by demodulation techniques, and it just matches the carrier, and then you get like signal 1, signal 2, signal 3, and signal 4. And like we have, whoops, oh no, there we go. We have these techniques, like we have these demodulation techniques, and in digital we can even still use it, because it's still like the carrier wave would be like this instead of a sine wave, would be like this. Let's say this is, and then the message is like another here, like lesser frequency, and then these two modulate together, and then you end up with it's just a multiplication, like this one times this one gives you let's see, this one 1 1 0 1, so this is 0 1 0, is still 0 0 0. I think this actually comes a 1, and 1 0 0 0 1 0, like that. And if you match it, like there's usually more waves, and then you match it with another carrier with a demodulation frequency, and then you get it back to the original signal. So we have these normal maps, and they're here. Like they store data in the baseband, so we store data in X and Y, and like this tells, depending on the UV mapping, like here's your new normal map, U1 quad, like this is your region here, and wherever this normal hits, then you put out either this data or this data depending on the angle. But the thing is that like that's in the baseband. Like we can probably actually store information here like at different frequencies. So we can like pack this, like we can pack this so hard with data, because like I don't even think anybody's doing anything like this. I don't even think it even occurred to anybody. And like cell phones already do this. Cell phones like modulate signals this way, and if I can find like a way to store data in a normal map that's like can give more fidelity, like even though the cosine, the uh the dot product of the cosine is like this, like if even a small amount of data was stored in a different frequency, like for these extreme angles that don't really happen that often, like the bandwidth of data that's stored in the normal map, like it can be, I don't know, like 1,000, 2,000, like we have 4K textures now. Like the sky's the limit. Like that's a lot of pixels. And I don't know. I don't really understand how normal maps store things yet. I've been trying to find the equations, but I guess they're paywall in universities, or maybe it's not super common knowledge exactly how normal maps are made. I know that it's like object dependent and surface dependent. I haven't been able to find any of that information. I really want to because uh, there there might be a way to put modulation techniques in the way that we store textures, and then like that's a lot of data, and the trade off will be more compute power. Great, more raw compute power is going to be needed in real time. Uh, but but our the hard disk space is going to be like way way smaller. Like the trade-off is ridiculous. If we can store like information in here in a modulated way, I don't even know how many arrows I can draw. like this is one bad thing that we have to compute more things in real time, but it's also in real time. So if you can put it into your compute budget in real time and just like account for it, like the hard disk space, like it can use like compression algorithms to like store things in real time and have things be demodulated in real time, and like get more data into like these edge cases of the normal map. Like like there could be so much data in here. Like this here is like a lot. Like anyways, that's what I have like been obsessing over, and I've been trying to figure out how how to store this data in there. And the closest analog that I can come up with is uh, lasers. Like so, they're in there's a type of holographic laser storage device. So it's a brick of some element. I forget what. I don't know if it's beryllium or what. So there's like a brick, and every it's doped. It's doped with something. I think it's iron. I think it's iron plus two or something. And there's two lasers that shine on it, and depending on where these lasers intersect inside of this three-dimensional space, like you can store a bit right here, like right where they intersect. That's one bit, but then there's another one here, another one here, another one here, another one here, and like one of them's a reference laser, so it's kind of like a carrier wave, and then this one puts out a one or a zero at a certain frequency, like, and then it'll trap an electron in this iron impurity. So I was thinking that we have a normal map, and it does whatever it do. It does whatever it do. But then the viewing angle upon which we view something can also be like these two lasers, because here's this can be x and this can be y, and whenever we have a viewing angle, there can also be an x and y depending on how it hits the surface. Because like, well, if there's an angle theta, right, and so this has an x and a y component, or if you're in Unity, backwards land, it's, it's gonna be, what is it, z and y, okay, because x is the other coordinate. Um, the viewing angle can act like these two parts of a laser, and then the normal map, like the the one of them, the x coordinate, can be like the carrier wave, and then the other one can be like the I can just read the signal, and like the normal map can have like a lot of depth. Like on the surface, the normal map is like this, just like what it usually reads for its calculations and stuff. But the thing is that using modulation techniques, you can actually store information inside of signals below the noise threshold. So, like one example of this is the Voyager satellite that I think already left the solar system. And one of my professors from Cal Poly was talking about it, and I remember this very distinctly. So he was just chit chatting with us in class. So for Voyager, from outer communicating with us from outer space, sending us signals, the uh, the noise threshold is here. The noise threshold of outer space is here, and the signal that Voyager changes is over here. It's like not even perceptible because it's on a logarithmic scale. It's like it's log, not even base 10, log natural log. Um, it's like imperceptible, but somehow it makes it back literally from the furthest ranges of humanity back to the Earth, and like the so this could be the baseband of the normal map. And then over here we can store even more data for these edge cases of the extreme angles. And like the normal map itself wouldn't even notice because if you do the encoding properly, even if you put a coherent signal in there, there's modulation techniques to scatter this signal so that it appears like even more noise. So like the signal will be stored here or here because it's like in the frequency domain. When you modulate a frequency, like in the time domain, like it's scattered, so it'll just look like random noise, and it won't individually. Each normal map at the baseband won't really be affected by that much. It's gonna be less than 1% unless you like really pack a lot of data in here to create like huge conglomerations of data to like twist the normal maps around. It's gonna be like these little interspace dots. So like a normal might be like what, like a 0.5, and now because we'll be adding like 0.00000001 to it, like it's not even gonna appear during runtime. But then if you put a decoding frequency in it, like it'll go through the frequency domain and gather all these data points and then produce a coherent signal, and like you get your data out of there. Like yay, more free data out of the same texture, like no additional hard drive space. Yeah, it's free. Well, not free data. We had to introduce like a little bit of noise into the normal map, or an image texture or anything. But it can also be the only problem that I have is that how do you read this in runtime? Because these types of decoding signals require probably at least 8 capture points of data. So, like, I don't want to make an 8 pass rendering just to get this information for the edge cases. So, hopefully, there's a way to do it um, in parallel. I mean, we have GPUs, and it's not really a signal that we're waiting to receive over time, like a phone transmission. Like the data already exists here, like all the time. Oops, not ready anymore. There we go. So I was thinking the demodulation blocks usually look like this. So there's a Z to the why is this appearing? This is so annoying. Stay there. Okay. The blocks for demodulation usually look like this. Shoot, this is in the way. Is this? The way to demodulate these signals actually isn't that difficult. Oh, I am my graphics card turning on. It does not like me writing this much. But the demodulation techniques are like this. There's like a signal comes in, a modulated signal comes in, and this like let's just say it's a digital signal, and it goes into here, and there's like a series of blocks. Like this is a digital filter, and inside of each one of these blocks is just a delay. This just means z to -1 means that it'll slow down. It'll just store the data for one clock cycle, and then during the next clock tick, it'll spit it out to the next one. And then this one stores it for one, and then this one stores it for one. And here is a multiplier. So it's just a constant. I mean, unless you make a fancier filter. So this constant one, constant two, and then it just like cascades like over here, and then there's like another z to the negative one. Here's a multiplication node. This one sends data there. Here's another multiplier, and then here's another one. And then this one has its own thing over here. And then finally a fancy nice signal that's like, yay, we have a signal. But all these are delays and multiplications. So C1 can be from -1 to 1. And there are some rules to setting up these kind of filters so that it doesn't go into an unbound condition, because these are multiply and add. So this times this times this, and then this is addition. But really, in shader graph, it would just be like these blocks. Shader graph already has something like this. Like this would be a multiply. So multiply. This is like this part right here, and then addition. Like it already stores data, because every time it has to compute like the next line of code in C, it's like a delay. Like it depends on how you hold the data. Like all of these are just multiply and additions, and with some fancy techniques, you get a demodulated signal, and then you can get data out of stuff. The only question is like how. So I'm trying to get more information on how normal maps work, and see if I can make this work in Unity in real time. I don't know. It's crazy. I hope that normal maps aren't already this. I hope that normal maps aren't already a version of this, because I know that the way that they work is not linear. So I hope I'm not gonna roundabout rediscover normal maps or something similar to it, because like these kind of filters, uh, they're just like they're digital equivalents of integration and the DX functions. If you just do, because what's integration? Integration in the digital domain is just a summation. So from n equals 0 to whatever 500, like that's integration. What's dx? Dx is data point 2 minus data point 1. Wow, so amazing. Like these filters can easily accomplish these operations, like not exactly. And I don't know, all sorts of analysis in digital are done using really simplistic dumb methods, like Fourier analysis to do frequency decomposition. It's like a series of these delayed things, like the z is -1. Like there's like a butterfly pattern that you set this up with, and it's like something like this. Like I'll just like do it real quick, like this, like this, like this, like this, and it'll like it's really slow. There's like an optimized fast Fourier transform, but the regular Fourier transform in digital is like just like a bunch of switching blocks in a certain order that subtract and stuff, and then at the end you get a frequency spectrum, and it's freaking dumb. Like I can't believe it works. It's so dumb. Like a bunch of additions and minuses, and like I don't even do like modulos in there, which is like multiplication and delays, and then it pops out your signal. Like, oh, here is your signal. Like, yes, at frequency 10K there was a 1. Like, yes, there you go. At frequency 20K there was a 0. Like in this signal. Like at this exact moment. Like it's like I really hope I just don't rediscover normal maps. Like if I go through all this trouble and rediscover and find out that Like I just rediscovered something that's really common. Like it's gonna really piss me off that I like thought this was a good idea. Like this that'll suck. It's very possible. Like it's really possible. Like there's probably also a good reason why normal maps are terrible at small angles, and I don't know about it because I don't know anything. So whatever, I'll find out when I find out. Either I can do what I'm trying to do, or I can't.